Okay, let's continue with structure and interpretation of computer programs. We arrived at section 3.3, modeling with mutable data. So, chapter 2 dealt with compound data as a means for constructing computational objects that have several parts in order to model real-world objects that have several aspects. In that chapter, we introduced discipline of data abstraction, according to which data structures are specified in terms of constructors, which create data objects, and selectors, which access the parts of compound data objects. But we now know that there is another aspect of data that chapter 2 did not address. The desire to model systems composed of objects that have changing state leads us to the need to modify compound data objects, as well as to construct and select from them. In order to model compound objects with changing state, we will design data abstractions to include, in addition to selectors and constructors, operations called mutators, which modify data objects. For instance, modeling a banking system requires us to change account balances. Thus, a data structure for representing bank accounts might admit an operation set balance. That changes the balance of the designed account, of the designated account to the designated new value. Data objects for which mutators are defined are known as mutable data objects. Chapter 2 introduced pairs as a general purpose glue for synthesizing compound data. We begin this section by defining basic mutators for pairs, so that pairs can serve as building blocks for constructing mutable objects. These mutators greatly enhance the representational power of pairs, enabling us to build data structures other than the sequences and trees that we worked with in section 2.2. We also present some examples of simulations in which complex systems are modeled as collections of objects with local state. So, mutable list structure. The basic operations on pairs, cons, char, and coulter, can be used to construct list structure and to select parts from list structure, but they are incapable of modifying list structure. The same is true of the list operations we have used so far, such as append and list, since these can be defined in terms of cons, char, and coulter. To modify list structures, we need new operations. The primitive mutators for pairs are setChar and setCoulter. SetChar takes two arguments, the first of which must be a pair. It modifies this pair, replacing the char pointer by a pointer to the second argument of setChar. As an example, suppose that X is bound to the list A, B, C, D and Y to the list E, F, as illustrated in figure 3.12. Evaluating the expression setChar xy modifies the pair to which X is bound, replacing its char by the value of Y. The result of the operation is shown in figure 3.13. So I expect that instead of ABCD, we will find EFCD. Let's see if I'm right. The effect. What the F is that? Okay. Let's continue with the reading, and then we will see. The structure X has been modified and would now be printed as EFCD, as I told you just before. The pairs representing the list AB, identified by the pointer that was replaced, are now detached from the original structure. Compare figure 3.13 with figure 3.14, which illustrates the result of executing define Z cons y coulter x with x and y bound to the original list of figure 3.12. The variable z is now bound to a new pair created by the cons operation. The list to which x is bound is unchanged. The setCoder operation is similar to setCar. The only difference is that the CUDR point of the pair rather than the car pointer is replaced. The effect of executing setCoder xy on the lists of figure 3.12 is shown in figure 3.15. Here, the CUDR pointer of x has been replaced by the pointer to EF. Also, the list CD, which used to be the CUDR of x, is now detached from the structure. Okay, this is seems to be very easy and very straightforward. Cons builds new list structure by creating new pairs, while setCar and setCoder modify existing pairs. Okay? They are indeed mutators. Indeed, we could implement cons in terms of the two mutators together with a procedure getNewPair, which returns a new pair that is not part of any existing list structure. We obtain the new pair, set its current CUDR pointers to designated objects, and return the new pair as the result of the cons. Okay, seems easy. An exercise, more exercises. Okay, sharing and identity. We mentioned in section 3.1.3 the theoretical issues of sameness and change raised by the introduction of assignment. These issues arise in practice when individual pairs are shared among different data objects. For example, consider the structure formed by define x, define z1, okay, shown in figure 3.16, z1 is a pair whose current CUDR both point to the same pair x. This sharing of x by the current CUDR of z1 is a consequence of the straightforward way in which cons is implemented. In general, using cons to construct lists will result in an interlinked structure of pairs in which many individual pairs are shared by many different structures. In contrast to figure 3.16, figure 3.17 shows the structure created by the definition of Z2. Yeah, basically here we are not using x as alias, so we are not using x as a variable, but we construct the pair using the directly list of A and B. In this structure, the pairs in the two AB lists are distinct, although the actual symbols are shared. When thought of as a list, Z1 and Z2 both represent the same list, AB, AB. AB, AB. Not clear why AB, AB. Why AB, AB? Shouldn't be AB in brackets and AB also in brackets? Is that implicit? Because it's a pair and thus more parentheses will be redundant? Probably it is. In general, sharing is completely undetectable if we operate on lists using only cons, car, and CUDR. However, if we allow mutators on list structure, sharing becomes significant. As an example of the difference that sharing can make, consider the following procedure, which modifies the car of the structure to which it is applied. Set to wow x, set car x, wow x, okay. Okay, figure. Even though Z1 and Z2 are the same structure, applying set to out to them yields different results. With Z1, altering the car also changes the CUDR, because in Z1 the car and the CUDR are the same pair. with Z2, the car and CUDA are distinct. So set to 1 modifies only the car. I see. Okay. Makes sense. Makes absolutely sense. Because in Z1 these two guys share the same pointer, right? In this case the pointers are different, so when you act with set to wow on the car of Z2, you are only modifying the one value and not the other one. Okay. One way to detect sharing in list structure is to use the predicate AQ, which we introduced in section 2.3.1 as a way to test whether two symbols are equal. Let me check one thing, sorry. Let me check one thing. Okay. Everything is working. Okay, more generally, EQ tests whether x and y are the same object. That is, whether x and y are equal as pointers. Thus, the comparison is not between the values, but between the pointers, which is an entirely different story. Thus, with Z1 and Z2 are defined in figure 3.16 and figure 3.17. EQ car Z1, CUDA Z1 is true, and EQ car Z2 and CUDA Z2 is false. Yeah. As will be seen in the following sections, we can exploit sharing to greatly extend the repertoire of data structures that can be represented by pairs. On the other hand, sharing can also be dangerous since modifications made to structures will also affect other structures that happen to share the modified parts. The mutation operations, set car and set CUDA, should be used with care. Unless we have a good understanding of how our data objects are shared, mutation can have unanticipated results. Okay, and this is basically this applies every time you use pointers and you try to use languages such as C or C++ or even Golang and Rust, where you have pointers, and in these programming languages you really have to understand what you are doing. It's not like Python, even if also in Python you can do disasters if you do not understand these concepts of pointers and how values are allocated in the memory of the PC or the computer. So let's go on. We have a bunch of exercises, and now we have this section. Mutation is just assignment. When we introduced compound data, we observed in section 2.1.3 that pairs can be represented purely in terms of procedures. Yes. The same observation is true for mutable data. We can implement mutable data objects as procedures using assignment and local state. For instance, we can extend the above pair implementation to handle set car, and set CUDA in a manner analogous to the way we implemented bank accounts using make account in section 3.1.1. Yeah, I see the point. I see the reasoning behind this. Assignment is all that is needed theoretically to account for the behavior of mutable data. As soon as we admit set to our language, we raise all the issues, not only of assignment but of mutable data in general. Okay, section 3.3.2. Let me see how many subsection there are in 3. Okay, representing queues, tables. Okay, then we have concurrency and streams. Okay. Okay, let's continue. Representing queues, the mutator setCar and setCoder enables us to use pairs to construct data structures that cannot be built with conscar and coder alone. This section shows how to use pairs to represent a data structure called a queue. Section 3.3.3 will show how to represent data structures called tables. A queue is a sequence in which items are inserted at one end, called the rear of the queue, and deleted from the other hand, the front. Future 3.18 shows an initially empty queue in which the items A and B are inserted. Okay. Then A is removed, C and D are inserted, and B is removed. Because items are always removed in the order in which they are inserted, a queue is sometimes called a FIFO or FIFO, first in, first out buffer. In terms of data abstraction, we can regard the queue as defined by the following set of operations. A constructor, make queue, returns an empty queue, so a queue containing no items. Two selectors, empty queue and front queue. The first one tests if the queue is empty, and the second one returns the object at the front of the queue, signaling an error if the queue is empty, and it does not modify the queue. And then two mutators, insert queue, taking two arguments, queue and item, that inserts the item at the rear of the queue and returns the modified queue as its value. And delete queue, which takes as argument only the queue and removes the item at the front of the queue and returns the modified queue as its value, signaling an error if the queue is empty before the deletion. Because a queue is a sequence of items, we could certainly represent it as an ordinary list. The front of the queue would be the car of the list, inserting an item in the queue would amount to appending a new element at the end of the list, and deleting an item from the queue would just be taking the coder of the list. However, this representation is inefficient because in order to insert an item, we must scan the list until we reach the end. Since the only method we have for scanning a list is by successive coder operations, this scanning requires on steps for a list of n items. A simple modification to the list representation overcomes this disadvantage by allowing the queue operations to be implemented so that they require O1 steps, that is, so that the number of steps needed is independent of the length of the queue. The difficulty with the list representation arises from the need to scan to find the end of the list. The reason we need to scan is that although the standard way of representing a list as a chain of pairs readily provides us with a pointer to the beginning of the list, it gives us no easily accessible pointer to the end. The modification that avoids the drawback is to represent the queue as a list, together with an additional pointer that indicates the final pair in the list. That way, when we go to insert an item, we can consult the rear pointer and so avoid scanning the list. A queue is represented then as a pair of pointers, front pointer from PTR and rear PTR, which indicate respectively the first and the last pairs in an ordinary list. Since we would like the queue to be an identifiable object, we can use const to combine the two pointers. Thus, the queue itself will be the cons of the two pointers. Figure 3.19 illustrates this representation. Okay, seems pretty reasonable. To define the queue operations, we use the following procedures, which enables us to select and to modify the front and rear pointers of a queue. Now we can implement the actual queue operations. We will consider a queue to be empty if its front pointer is the empty list. The make queue constructor returns as an initially empty queue a pair whose car and could are both the empty list. Okay. To select the item at the front of the queue, we return the car of the pair indicated by the front pointer. That's reasonable. To insert an item in a queue, we follow the method whose result is indicated in figure 3.20. we first create a new pair was car is the item to be inserted and was coder is the empty list. If the queue was initially empty, we set the front and rear pointers of the queue to this new pair. Otherwise, we modify the final pair in the queue to point to the new pair, and also set the rear pointer to the new pair. Okay, this is very easy. To delete the item at the front of the queue, we merely modify the front pointer so that it now points at the second item in the queue, which can be found by following the coder pointer of the first item. Okay, some exercises, but this is easy stuff. I think we can stop here for today, and the next time we will see how to represent tables. So see you in the next video.